Hi everyone. Today we're going to learn a process for finding the derivative of a function called implicit differentiation. And so before we jump into it, we're going to kind of revisit our basic method we have for finding the derivative of a function, and we'll talk about why we need implicit differentiation. So the first question asks me to find the derivative of y with respect to x for the following function. Now the first thing I notice when I look at this function, number one, is that y isn't by itself, which we're always used to seeing. Now the good news in this case is it's really easy to get y by itself, so I'm going to do that first. And I'm going to subtract the 3x squared from both sides. I'm going to move this over. So I have y equals negative 3x squared plus 2x minus 7. So then to find the derivative of y with respect to x, our dy dx, I'm just going to use our regular old power rule. So I'm going to get negative 6x plus 2. So that one, even though y wasn't by itself right away, it was really easy to deal with and use the rules that we have. Now, what we're going to start encountering is functions that are defined implicitly. Right, so we're talking about implicit notation for a function, and this is when a function is not written with y by itself. So an example might be, x squared plus y squared equals 25. Right, so when I look at that, I know y is not by itself. Now, sometimes, like up here, it's really easy to get y by itself first. However, sometimes it's much easier to take the derivative that's defined implicitly if we don't have to solve for y first. And this is where implicit differentiation comes in. So in these types of problems, anytime we take the derivative of y, we need to write dy dx to represent the derivative of the function that y represents. And we'll talk about this when we get into some problems, but really there's kind of some chain rule going on here. Once we're able to take the derivative, we need to get the dy dx isolated, because that's what we're trying to find the value of. So we can tell we need to use this technique because the function will be defined implicitly. And again, what that means to us is that y is not by itself. So whenever y is not by itself, we're going to use this implicit differentiation. Alright, so for number one, okay, and actually this is the example I wrote above, we're going to use implicit differentiation to find dy dx. Okay, and so what we're not actually going to try and get y by itself first, we're going to use this new method. So here's how this goes. I'm going to take derivatives like normal for any term that does not have a y in it. So for example, when I see x squared, I know the derivative of y with respect to x is just 2x. Now, my next term has a y here, so that really represents a different function. So what's going to happen here is I'm going to take the derivative like normal using power rule, so plus 2y, but then I have to tack on a dy dx. Because again, this represents taking the derivative of the function represented by y. Now I'm going to do equal, and I'm going to take the derivative of the right side. Since that's a constant, its derivative is 0. So that was really step one. Taking the derivative, writing dy dx when we take the derivative of y. Now our next goal is to get the dy dx by itself, because that's what we're trying to find here. So in this case, I'm going to take everything without a dy dx and I'm going to move it over. So I get 2y dy dx equals a negative 2x. The next thing I have to do to get dy dx by itself is I'm going to divide by this 2y. So those are going to cancel, and I'm going to get dy dx equals, my 2's are going to cancel, so I'm going to get negative x over y. Now I've isolated dy dx, and so I have my derivative. So you'll notice now these look a little bit different, because before when we took derivatives, we didn't have a y in the derivative, but now we will. All right, let's look at another example. Okay, now we have x plus the tangent of xy is equal to 0. So we're going to do our same implicit process here. So the derivative of x I know is just 1. Now here I can see I've got some chain rule going on. So my outside function is tangent. So I know the derivative of tangent is secant squared. When I do chain rule, I know my inside stays the same at first, so I have secant squared of xy, and then I have to multiply by the derivative of my inside function. So now there's a few things going on. In my inside function, I have the product of x and y, so I need to use product rule, and I have a y, so I need to do implicit differentiation. So I'm going to multiply by x times the derivative of y, which is just going to be dy dx, plus y, my second function, times the derivative of x, which is just 1. And now that's equal to 0. So I can simplify a little bit. I have 1 plus secant squared of xy times x dy dx plus y is equal to 0. And now my goal is to get my dy dx all by itself. So I'm going to kind of have to work from the outside in here. So the first thing I'm going to do is get rid of this positive 1. So I'm going to have secant squared of xy times x dy dx plus y is equal to negative 1. Now, I'm going to get rid of the secant squared of xy. Since these two factors are multiplied together, I'm going to divide by my secant squared. So I'll have x times dy dx plus y is equal to negative 1 over secant squared of xy The next thing I'm going to do now is subtract y from both sides. So x times dy dx equals, let's see, I've got negative 1 over secant squared of xy minus y. And then the last thing I'm going to do is divide everything by x. So my dy dx is equal to negative 1 over secant squared of xy minus y all over x. Now, that one is obviously pretty complex. There's a lot going on, right? We have our chain rule, we have product rule, and we have implicit differentiation. Now, my guess is at this point this video has generated enough questions that I'm actually going to stop it there. We'll make it a short video. When we're back in class, we'll address any questions that came out of these two examples, and then we'll look at what happens when we have to take a second derivative where implicit differentiation comes in. So we're going to leave it at that for now, and I'll see you back in class. Thanks.